No.
Hello. I think we both got a haircut.
Yeah, it's prepared for the summer.
Yeah.
I had a call with Michael, and then all my hair fell out. So that's what happened.
I wonder if the AI will summarize our hair discussion.
Maybe. But the AI actually thought for the last couple of months anyway that I don't have any hair.
Hi
So
everyone.
I thought like maybe the AI is right, so I just cut it off. But there's this built-in image optimizations into all of the cameras, especially the Apple webcams and iPhones and also Samsungs. It's actually not like the picture that you take, it's a highly optimized, AI optimized picture. And these webcams and the image optimizations, they always render my hair away. So
Oh.
then it looked like that I didn't have any hair. So I thought, you know what, maybe it's a sign.
Oh, so it's not AI rendered anymore. It's now really off.
Yeah, it's actually
Yeah.
really off now. Yeah, I cut
Yeah.
it off.
Yeah. And Mike also has a full head of hair in real
Yeah,
Yeah.
life.
it's just AI. Yeah, we actually look
Yeah.
like Camille. Actually, it's just AI which removes it.
I can take it off if you want.
I would have been so funny if you actually just did that, you know.
Or
And
yeah,
it's just to pay.
I'm hiding things anyway, you know.
Yeah, yeah. I gave up with this. I just
I'm
accept.
still fighting.
Let me just get everything ready. By the way, we have a relatively good notes from the AI, so I will add that to the repository as a pull request, and then everybody can go over it. And if you're okay, we can merge it. And then next week we will have a better process for that, so that it's
And we
there.
now use AI to clean up the notes that the AI did.
I just um, while I'm looking through that, 1 second. So it actually looks pretty good. Like it has here also next steps. Like it tracks our action items.
Hmm.
Oh yes,
Because-
it did.
So it follows these things, which is brilliant, right?
So the AI did, but I didn't.
Yeah, no, but this is good.
Yeah.
But I will drop it into a pull request, and then everybody can have a look. If it's good enough, we can also auto commit it. But like for the next 2 or 3 times, I will do a pull request, and then we can quickly go over if everything is okay or if it just did something crazy. Because I think this can be a good addition. And help also to recap a bit. So, okay, are we complete? 1, 2, 3, 4, 5. Okay. Wait a bit more.
Yeah, I think we're missing
Yeah,
Derek
2 more
and
minutes.
Sachin.
Yeah, let's wait 2 more minutes or so, and then can start.
Carmel, your plants are gone. Did they die?
Uh, I don't know. That's not me who maintain it, so I have no idea. I mean, I'm surprised every time I have to, water them. I find new ones. So
Ah, that's good. At least you watered them. They like this.
I mean, I suppose to, but
It could
you
also
can
be
tell.
time zones, right? That they are missing
Oh, yeah.
True.
because we switched now in Europe.
So they might
But
be
is
trying to join in an hour.
yeah.
Let me ping both of them and see if they're joining.
It was just a hunch because like we switched last week, right?
Oh, does this mean we have like a really late main
Oh,
version?
Sachin just DM'd me saying he won't be able to make the meeting this week.
Okay, don't worry. Okay, and let's just start. Or is Derek?
We can go ahead and get started, and he can hop back in if we need to. But I
Okay.
did send him a message.
Yeah, I had to search for him now. Okay. So let's start the meeting by reminding everyone that we all agree to the GraphQL spec membership agreement and the GraphQL Foundation Code of Conduct. All of these agreements are referenced in our agenda, so if you need a fresher, just look them up. Let's start with a quick round of introductions in the order of the agenda. My name is Michael, and I'm the host today.
Oh, Shane from Apollo.
Martin, also from Apollo.
Pascal from Chili Green.
Kamil from the guild.
We through?
I think so.
Yeah.
Yep.
Yeah. Okay. So we discussed last week satisfiability. I think this is also on the agenda for today. After this meeting, we will really start on specifying that. So start writing down the algorithms. Just a couple of things I think we have to discuss, and then we will start from there. And then it also, I think, becomes a bit easier once we have some written spec text on that to chime into several things there. But before we just go down a lane, I think let's finish the discussion on there.
Yeah, can you
So
be share rights?
yeah, let me give you that.
Just need to open the right files. Okay. So just as a recap, so we're all on the same page. The algorithm that we want to describe, what we discussed last week is that we have this plan option step. And the plan option step is essentially a function where we pass in a path and we get out the possible options where we can go and visit, or the possible options that we can be in on the different source schemas. And we also decided that requires will be handled in plan options, so we don't have to carry we don't have to care about requires in satisfiability. And the week before, we also ruled out that provides has any effect because provides is just metadata, so that shouldn't change the execution of this should change the execution, but shouldn't change the satisfiability itself.
So so plan option cares about requires means that it only will yield options that are satisfiable where the requirements are satisfiable within the current context.
Good question. Probably.
Yeah. I mean that's
Both.
what we do. Oh, go ahead.
I was going to say both provides and requires can be validated by just looking at the single subgraph schema. So in that sense, we don't need to satisfy with the entire set because you have to specify the inputs. If I say I provide some field and the field name doesn't exist,
Yeah, but
like we can check that when we're doing the first subrow check.
Provides is not handled in satisfiability. It's ignored in satisfiability.
And what we do need to do with requires is it affects which paths we're able, or which traversals we're able to take. Sort of whether we're able to traverse from like one subgraph to another depends on where we have access to the required fields at that point.
Exactly. That's what that was exactly my question, because like this makes the base algorithm much more simple, because you basically get the options that you can take. We don't care about requires. Like the plan options function will just only yield fields where we can fulfill the requirement at this point where we are.
Yeah.
Yes, and there's essentially, so requires would also mean that we do cascading requires in plan options. So if you need to go somewhere to get something, and then only then you can actually do the request, we will do this in plan options. So it's actually a bit of a execution planning logic that we have there. This will also be defined at the end. We just assume that this plan options function exists, and then we can still
Yeah.
decide what we'll do.
And it would sort of recursively call plan options for the required fields, right? That's the idea.
I mean, we may not even have to do this, right? Because it's just that there just needs to be the requirement itself is you have a requirement, and then the resolving of the requirement is a problem that the execution could solve. So we
No,
could,
but you
No.
need to ensure that you're actually able to satisfy
Yeah.
that requirement. So for instance, if you're in like A.B and you want to plan options A.B.C, and there's a field X that C requires, at that point you actually need to ensure that you can get to A.B.X, or maybe through an intermediate path.
but there we wouldn't work on the query paths, right? We can just say that, is there a way how we can get there?
No, but you actually need to
must.
take the whole query path into consideration, because that's the context you have.
That's
so you,
also
you,
what we. Yep.
Yeah.
Sorry. Go ahead.
Well, yeah, I'm just saying, so sort of there's a difference between getting X from A.B.X, or maybe getting it from like A.E.X. That might be an entirely different way of getting that field. Maybe you're even going to a different subgraph because you have a different key available to you, for instance.
Okay, but isn't require a local problem on the position that we are at the moment?
No, because whether you're able to fetch the required fields at that point depends on where you are in the path.
Oh yeah, that's, I mean,
Yeah, you need basically you take what is in require and you do a complete query planning on it. It's kind of like inlining the fields
Yeah.
there and see if you can get them resolved in order to get this other field actually resolved.
Yeah, with one condition, like you'd never fetch data from the subgraph you're in,
Yes.
and that's pretty much it.
Yeah.
Yeah, that's runtime optimization. But the plan, like I guess the satisfiability is still, we need to verify whether it's external or internal or not marked as external. You can still require it, and so I
Yeah,
guess it
but
does make it simple. If it's not marked as external, then you can get it. But
yeah, there's an issue. If it were only available on the same subgraph, it would not be resolvable on the runtime. It's not a runtime optimization. It would just not be satisfiable in that case.
I mean,
So
we
you
shouldn't go to satisfiability anyway when we have this, because that we have a validation rule that actually validates that you cannot require from yourself. It's
right.
it's very easy to write, but so Glenn, I write the rules, and Glenn implements it on purpose so that he needs to read. So this way we validate the spec essentially. And I added one sentence, was like, oh yeah, and you cannot require from yourself. And it was like, now I have to change everything I have implemented because that's a new requirement that came in. But anyway, yeah, so
Yeah, there is like in a query planning,
with local problem, I mean that when I'm here A, B, C. So I'm on field C, and we know that this is wrong how we've written it here because it's actually this. So it's A, B, and then I'm on field C on type B. And
Yeah.
local problem, I mean that you have to resolve the requirement at this position from source A or source B. And then if I can only resolve it from source A, then the plan options will only return source A. If I can only return it from source B or require it from source B, then. So with local problem, I mean is that you actually, this can happen inside of this plan options, right?
But it's a complete traverse. It's like to see if the query requirement is resolvable is basically the same graph algorithm.
Yeah, you just have a different starting point.
Yeah. So it's not just a function where it's like it's the same algorithm.
Yeah.
Yeah, and then it branches, so you
Yeah.
can require something that requires, and
And there might actually be cases in the future, and there are already cases currently for Apollo Federation where the entire path does matter, or at least more parents than just like the current subgraph you're in may matter, and that's when we use from context.
Context, right? Yeah. Okay.
Yeah.
And also probably data, right? No, for non-entity fields, it doesn't. It's because then you can also be deeper down, but that doesn't matter.
Yeah.
Yeah, it's not so complicated. Yeah, the context.
Yeah, we have something similar in Hot Chocolate where you basically you push something on a scoped context, and that is then available in the subtree.
Yeah.
yeah, it would also affect the override if we ever do one. But not override the regular one, but like the one that is called progressive override in Apollo.
Yeah, we
But
skipped progressive override for now.
yeah. Just saying that like it's one of the options, just like from context.
And it's good to keep those in mind, even if we're not specifying them right now, because it might affect the shape of the algorithm.
Yeah, that's true. That's true. So I would say we leave require out in the initial draft of the algorithm, so that we have an algorithm, and then we can see if we can just use the same algorithm for require inside of plan option. So it could be a cascading thing. But I think leaving it require out in the beginning probably makes the problem a bit easier to solve, and then we can see if I mean, it's not finished when we leave require out. We have to put require in, but it just makes the problem a bit easier to understand.
Yeah.
At first. Yeah. So another thing that we have discussed is that this is not enough, and that we actually want to have the full path. And Martin, you made a good comment last week that we can actually use the syntax for the selection paths. And
yeah, with the angle brackets.
Exactly. Yeah. And then we can work with this. So now proposal for this week would be to manually do a validation with the assumption to do a satisfiability check on a schema with the assumption that we have plan options, and just go through the steps and line them out to see what has to happen when, because that's the, I believe, the easiest thing to do. For this, we probably need a public schema. We could use this one if you want. And we probably also need some subgraph schemas. So interesting would be if we would run into issues where we have a loop and we need to detect a loop. That's probably could be done by having recursive types. And another thing would be interesting is when we we just need more fields than just a single root field to find out how we want to start the visitation.
I think let me quickly check, because we might because we defined a couple of tests. Did we just define test case for composition, or did we back then also define for planning? Let me check.
Planning, no, really. I mean, yeah, not really.
Yeah.
What about the like multiple fields? You just need to like basically the whole thing is about like finding at least one path for each requirement, let's say, and that requirement could be like a set of requirements, you know, like deeply nested structure, like the whole selection set, and we just find this and that, and then go deeper and deeper. And if we can resolve, like what I'm doing is like you have like a queue, like an array that you push and pop from, and then you know if it's empty, it means it was resolved. If it's you know not resolvable but still not empty, then you know we hit a dead end, so we cannot resolve this requirement. Then we cannot resolve the you know the required fields, which means we cannot really you know move to this edge and so on and so on. So
yeah, I think the implementation can be, in the end, it will be the root algorithm around it will be one of the graph algorithms like DFS, Dijkstra, or whatever. And it shouldn't actually matter which one you use, because it's just it must be a DFS algorithm. And then that should actually be fine. And we just need to get the loop detection in. No, the thing is, it would be interesting to see what do we need to do at what step. So you know when we should define a schema where we have lookups, and then try to make it a bit interesting to find out how this algorithm will actually work in practice. So let's think about this. Query is on both. A and B is in both.
Yeah, I think this is difficult. We would need to think about like because what you want is really specific cases to look at specific problems, Pascal.
Yeah, it might actually be better to just start collaborating on a set of test cases for this.
Yes.
That's also fine.
And then I think it might be better to do that like asynchronously.
Yeah. Yes. Because like we will not find one schema that like explains.
I don't even want to go into specific cases at the moment. It's more like how do we approach a problem? What has to happen when? So
Yeah,
like, you have a public schema, right, where you have these fields on. So the first step that you take is you take the first field of the query type and start traversal, right? And you traverse until you have either a leaf field that you can resolve, or you traverse until the set of options is the same as for a path that you have already visited, right? So this is the map that we have here. That's essentially, then you know you can stop and take the next field.
I don't think that we are getting there with a concrete example.
Okay.
Like what you actually look at is it's kind of a directed graph, right? We have three root types through which you can enter, and from these root types you dive into the graph, and then you look at the field and in which schema this field maps to, and you go each pass along, and every new type that you hit, you look at what fields you can resolve in which graph, and you try for each pass to see if it's resolvable. And if you find for each possible path, that there is at least one way to resolve it, then it's okay.
That's
So
satisfiability, yes.
yeah, but this is the base algorithm. I mean, there are lots of complexities in detail in, but I think what we should do is, but this is an async thing, and everybody can come up with a couple of edge case tests, with which we can actually validate the algorithm. But I don't think that we can start from a general purpose schema.
Yeah.
I think one of the questions there is also, do we want to go with sort of an abstract schema, like a type A and a type B, or do we want a like more of a domain schema that we can reuse throughout the spec?
I believe
Because I feel that does make it more readable and understandable.
I think
Yes.
we have the general rule that we use the bookshop examples. For execution, I believe we have defined once a schema which we want to share across all the tests, but we didn't do this in validation because in validation you often want to have one specific case, and if you want to have all edge cases of the of validation in one schema, then
No, I don't think it needs to be like one consistent schema, but these can be sort of variants of the same schema. So you can, like, if you reuse, I don't know, a book type everywhere or a store type everywhere, you can like make small modifications to it to fit a particular validation or a particular test case for satisfiability. But it's
Yeah,
still
we had
consistent within the whole schema.
Yes, and we like what we said is that we use this standard web shop schema with product and whatever, and we can use that in variants, and we can keep, if we want to show a specific problem, we just do a very small, the smallest possible schema setup to show this problem, but always in the same theme, if you will, right?
Yeah.
And then it's also, I think, it's much better to understand if we take concrete terms than A and B.
yeah, that definitely makes sense. But that's also something that we can do asynchronously. I think the general idea what we should discuss is how this generation happens so that we have a general understanding of it, right? So if we think about this as a graph and we visit the public schema, we start with the first field and then we essentially branch off the different options that we have there, right? So this is what
Well, no, I don't think we branch off the different options. We branch off the different fields that are reachable from the target of that other field. But we don't actually split option generation based on each option. Like we still go through path generation first.
yeah. But the path generation is that's also, I mean, that's the DFS algorithm, right?
Yeah, but it's based on the public schema, and it doesn't branch out based on options. It carries along the different options.
Yes, yeah, that's what I mean. I mean, when this is the public schema, so let's make this
Yeah.
just
So to be clear, like if you get to A dot B, and you can get B from like both subgraph 1 and subgraph 2, we don't actually branch off at that point. Like we just continue to look at the target of B and what fields are available from there, but we carry along the fact that we got there, or we are able to get there through two different routes.
yeah. And then so we BC, sorry, just like this bit. And from here we go to CD. Now we are at the leaf, right? And this is the first path that we essentially validated. So this would be the one that we have here. we're on query A, then we go to B,
Yeah.
then we go to C, then we go to D, and we have a complete path. And then essentially the visitation would essentially say that from BC we then actually reuse everything that we have, right? And just say that we also have to do the same for AA and go there further.
Or CE, I think, right? Because we're still at C at that point.
Yeah, that was wrong, sorry. BC. It's actually a good question. So that's this BA like this, right?
Yeah.
And here we would carry on with the loop detection. And essentially the whole thing will just be a simple graph visitation in the end, where we then start on B and do the stuff on B as well. And the output of this is actually exactly what we discussed, right? That you get a list of possible, I mean, you don't have to store this, but essentially in theory, you go through these different execution steps. This is also more or less what you do, right, Kamil? It's just a DFS algorithm.
Oh, I use BFS, but yeah, I mean, so like, I don't think it matters if it's DFS or BFS, to be honest. Like, it's just like you have to visit, like, what I do is like two graphs. One is the one that user can query, so it represents the thing you can introspect, which is like public schema. I don't have a name for it. I call it like super schema, but like it's this one, and then I just like go through the edges that are fields, like just just a regular field, and then it ends at like each edge has a head and tail, and then I just traverse, and then when I do the I call it moves, so I move into another position to another node or like through the edge, then I keep track of all the possible options. Yeah, per subgraph, I believe. So the shortest per subgraph. And then, yeah, if there's like no other options that allow me to move to another edge from this public schema graph or whatever, then it's a dead end, right? And that's it, pretty much it.
Yeah,
But
that was gonna be my suggestion as well. I think if you're trying to represent this as a graph, the better logical way that works best in code too is that nodes are the entire type, right? The type is the node, and then the edge is the path you're talking about. So it's the field A dot B is the edge that connects the node A to node type B. And so that's actually what you're constructing when you're building this, because when you do the other path, right, we're not going to duplicate the path that goes query.b and b.c. Once I get to type C, like it shouldn't be a new path. It should be connected to the other graph that is type C and all its possible ways I can get here.
It's like a smart query builder, no? Like you build a query as you go, and then it's like deeper and deeper and deeper, kind of.
Yeah. Yeah, we actually use that as output as well for error messages. Like we actually generate sort of a sample query when something isn't satisfiable, for instance, to tell you sort of which query would not be satisfiable.
yeah, but it sounds like the algorithm that you use is quite different from the Apollo algorithm and the algorithm that the guild's query planning satisfiability uses is quite different from each other, right?
We
Or
don't do the query planning. I mean,
and
it's
not the
kind of
query
planning, but like, yeah,
satisfiability.
satisfiability.
Because you don't like when we talked with Sachin about it, it's like you carry the state of the possible options along with.
Yeah.
So you only visit the public schema and you just carry the possible options along. Whereas what Kamil does in his implementation is that he actually you go into subgraphs, right? You first try if it works on A, and if it works on A, then if it doesn't work on A, you leave A and you try it on B. So it's the options that you have is actually very different. You
Well,
don't.
not necessarily, because we also need to like we also have sort of two. Well, our query graph has different levels, and one is the level of the API schema, and the other one is the level of the different subgraphs. So we do need to go into like subgraph A, for instance, its query graph to check whether a field is available there. Maybe the order of the visitation is different from what Camille is doing, but I think ultimately
No,
we
I
do
think
need to check the same data.
it just sounds as if you use different terms, because like the introspection schema is the public API,
Yeah.
and the moves is basically the options.
Yeah, we use the same representation for both. That's maybe it's what's confusing. We call these query graphs, and that's basically a graph representation of a schema. And we like as Shane was describing it, and we use that for both for the public schema, for the API schema, and for the subgraph schemas.
And to specify like the move, what I call is I have like super graph and merge graph, which is merge is like the state of subgraphs, and super graph is just like what you can vary, which is like not really good because the super graph, contains everything like it should by the name, right? So it should be really public schema, but just like I don't know,
Yeah, that's
giant POC.
that's what we call API schema. Maybe
Yeah.
we need to come up with a better name for that we can all agree on.
So what I wanted to say is like the move is actually like when you do the edge itself allows you to transition from one edge to another, right? So like it moves you somewhere. So I call it a move. And then there are multiple kinds of edges because you don't really have only fields, right? You can go from like an abstract type to like an object type, right? So you need to like encode that into the graph as well.
Yep.
Plus, when you have like interface objects, then it's also
and also
a
key traversal.
Yeah, exactly.
Yeah.
And then with the key, you connect the graphs and so on. It's like the whole graph actually explains the logic of the subgraphs and how they interact with each other. And then you just like when you do the traversal, you check can I visit the edge? Yes or no? If no, look for another thing. If yes, then please record why. I mean that I can, and then this is the path I took, and and that's basically what I'm doing. So I use BFS, DFS, I believe, depth first, but for some other things I use BFS. Oh yeah.
I mean, it all sounds very similar to what we were doing, and I think the question here is sort of what's the right level of abstraction to describe this in the spec, because this is probably too detailed or too specific, because there are likely to be good variations on this that other people may want to try out. So can we find the right level of abstraction to describe this?
Yeah, so this will be hard to specify, of course.
Well, I mean, the assumption is that sort of information is available to this process,
Yeah.
that it is able to check whether, for instance, type A in subgraph 1 has field F. I mean, that's just basically a query that the system needs to be able to answer. But we don't need to specify sort of how that is encoded. Like in our case, it's represented as a graph itself. But there's no, like, in theory, you could just like reparse the SDL every time it needs to answer that question.
Yeah, we can have some helper functions there.
Yeah.
I mean, we could specify it in the two steps. Like, we have the general visitation of the API schema that we describe here. Then we have this plan options thing, and maybe we get away with this, that it makes sense from a spec terminology, because you can and you don't want to specify the whole algorithm.
No.
You just want to we need to have an algorithm which covers all the cases and makes sense.
Isn't the query graph thing we're just talking about, this is just GraphQL satisfiability though, right? Like if we don't have like the drawing you have on the right, like if it's not a valid graph, it's not a valid GraphQL schema, and like the GraphQL validator itself would catch those things.
Yeah.
What we need to validate is the plan options, which take into account the composition specific things, which is that the fact that I can make other jumps with keys and interface and all the other things that can happen.
Yeah, it's also are the lookups there to cross over at certain points to reach certain information, right? Or can you get the keys for the lookups that are there to cross over? Things like that. That's actually what needs to be satisfied.
Yeah.
Yeah, I guess my point was that just the one sentence that you made there, Pascal, that we should check the API schema or the query schema, or what we call it. Like
Yeah.
we don't need to do that because like
Oh.
that is GraphQL's validations.
No.
I think what you meant, Pascal, was we traverse the public API schema and see if we can
satisfy
get
all the paths. So I'm not sure. So the thing that we have discussed is essentially that we have what we need to have is a list of possible paths, and when all possible paths are satisfiable, the schema is satisfiable. So to generate a list of all possible paths, we have to traverse to all combination of fields. And this is the loop that we were talking about, where we came up with this. We start with the visitation, and then we do on query A, on the query.a field, we do a plan options, which essentially outputs us what options do we have, and this is then stored on the context that we have in the visitation. And then we go from there, we go further and further, because as said, there's the case where we know that this path is complete and satisfiable when we enter a leaf field through any of the options. We know that we are in a loop and we can stop visiting. That's what Sachin put in last week, is that we can stop visiting if the options stay the same or are bigger, because we already have visited exactly this combination. And yeah, that's essentially it. And then we just have to continue as long as there is this specific type was not visited before with these options. And then with this, we may get away with quite a simple algorithm for satisfiability in general without the plan options. And then what we do in the plan options is up for debate. But generally, what we would have to describe in the specification is how we imagine that this visitation works, and then that we have a map of type to a list of lists, or to a list of set. And then this could already be specified.
Yeah. I would. I mean that maybe that's too detailed to comment here, but instead of a list of sources, I would talk about options, and maybe just define sort of what a set of options means somewhere else, so we can reuse that instead of specifying a concrete data structure.
So you mean instead of this, you would say options?
Yeah, and it doesn't even have to be a list. It's probably a set, like abstractly. So just to get away from specifying a concrete data structure, we can just say there's a set of options.
We use this algorithmically in the spec all the time, because for a developer, it's easier to understand what you're talking about. Doesn't mean that you have to implement it this way, of course. It's just, it's easier to talk when you talk about lists and sets, that you add this to the set of possible options, then it's very easy to specify. Because essentially this in from specification term point of view, this is or this doesn't matter which one we use. It's very easy to talk about, right? So when we can describe this in algorithmic terms, and then we can say in this case, like after this step, we add source A and source B to the list of options in A. And every time that we do a visitation step, we can check that here, for example, we are on C, and this is our context object. Do we already have C with these options? If yes, then we can stop the visitation because we have detected the loop. And then essentially the whole satisfiability algorithm breaks down into how do we traverse the graph? What are the stopping conditions? And there is currently 2 stopping conditions. The stopping conditions is actually 3. The stopping conditions is the list of options is empty, then we have a satisfiability error. The list of options is any number, but we are in a leaf field, then we are satisfied. Or the list of options is the same as something that we have already visited, then we are in a loop. So it's these 3-4 things that we have to specify and put in algorithmic text, and then the satisfiability should already be quite complete, except for the plan options, but we save this for the
Except for the the really hard part.
Yeah, I mean,
No.
the plan options, we talked about this before, right? Plan options could potentially also be that we say that we run the query planning for it, which none of the implementation does. But from a point of view of the specification, it's fine to ask the query planner to give the set of options. Do you actually do this? Do you use the actual query planner to verify when you have a path? Do you use the query planner to verify the options, or do you do it similar to Camille, where you aggregate the state on the fly?
Yeah, I mean they share a lot of the underlying data structures and functions. So this abstraction of a query graph and operations on a query graph, I think they're shared between composition and query planning, basically.
For example, give me the possible lookups for this specific field in this context and so on, right?
Yeah, things like that. But we don't actually we don't literally run query planning.
That would be incredibly inefficient.
Yeah. Well, especially because they have different purposes, right? So for query planning, we're trying to find the most
The best.
efficient, or like the best possible plan. And for satisfiability, we only need to ensure there's at least one.
Yeah. And that's also about exit strategies, right?
Yeah.
Satisfiability can exit much earlier than the query planning.
Exactly.
That's a good point. How many satisfiability issues do you track in composition? When composition fails because of satisfiability, do you calculate all of them, or do you stop after you found the first one? What's the output of the CLI when you have more than one satisfiability issue? Do you see all of them?
Ah, you mean okay. When you found that the path is not satisfiable, do you exit immediately, or do you look for all satisfiability problems? Is the question.
Shane might have a better idea. I think we only generate one, like we exit early,
Yeah.
but
I think we do.
Yeah.
Yeah.
Or Derek, I think you're also on the call. Yeah.
Sorry, I got distracted. What was the question?
Do we
There's lots of stuff happening right now, so that's like.
Do we exit early as soon as we find sort of one satisfiability error, or do we continue and like generate all possible satisfiability errors, or multiple ones, like according to some limit?
It's a great question. I think it is actually we're exiting as soon as possible, but
That's what I thought. Yeah.
It also makes sense. it also makes sense because that's also for the validation rule to specify very easily. As soon
Yeah,
as you-
for the specification, yes. User standpoint could sometimes be good to
yeah,
have
the user
multiple.
for the user it's shit, but it's also you have to. It's the same with the validation rules. If you follow the specification clearly, it could be that you run into an issue with with the source schema validation. Then you run into an issue with pre-merge validation. Then you run into an issue with post-merge validation. And only after you fix this one, you will run into the satisfiability issue. So if you follow the specification blindly, then you will have cascading errors anyway. I know that you actually, I believe you find all of the composition errors before the satisfiability in one batch, right? And then from
So yeah.
This is why you need great dev tooling, so you can do this all in your IDE.
Yeah, I mean compilers do that all the time, right? There's a syntax node that is expected but is missing, and then you just substitute it in the compiler, track it as an error, and move on. But that's dev tooling. I agree. Like we focus on first exit.
yeah, we'll start. We're on time anyway soon. We'll start this week with the satisfiability implementation with the new spec. And we probably get a bit more deeper understanding of it, and I will try to get this into some algorithmic form that we can review next week, just so that we get an understanding if this is actually possible to do.
Yeah.
It's really just these three conditions that we have to validate, and the general visitation, then I believe it's probably specifiable. Yeah. By the way, on another note, there's going to be 4 new validation rules coming. So the same set of validation rules that we have for require and provides, we will now also introduce for is, so that the field is selected, the correct field is selected and whatever, and they will do the same thing in reference to selection map specification for detailed analysis of this.
Should we review them next week, Pascal? Then we can go
To be
over
honest,
them.
these are going to be quite easy. I have an issue on GitHub to write them. I just do them when I have time. I would actually prefer to push this a bit. So if I get the time, I will write the validation, the first draft of a possible satisfiability algorithm validation in this very, very simple form that we have discussed it now. And then we can actually keep moving there.
I mean, we can also just maybe we should just post them, at least the GitHub links into the Slack channel. Then review can also be always async.
Yeah, true. Yeah, I just need to find the time to do it. But yeah, it's the next big chunk, and I think we simplified it a lot the last couple of weeks, how we can specify it, and then be great if this is in. Then once this is in, we can start talking about execution.
Awesome. Okay, then does anybody have something else, or shall we conclude? No?
No.
Okay, then we can finish, and hopefully we have next week something to review. I will put the pull request in tonight for the AI summaries. So if you have some time, just look at it. If we all think it's useful, I think it could be a good addition to the meetings. Awesome.
Great. Well,
See you next week.
See you all next week.
All right.